section 10.3, Notes on Taylor's Theorem. So we have been creating series to represent functions, and then we can use a Taylor polynomial to approximate a function by truncating the series at some term in the series, given an order or a degree that tells us when to truncate the series. When we do truncate the series, it does introduce some error. And so today we're going to talk about how we can approximate the error that we have by using a Taylor polynomial to approximate a function. So we'll start today with looking at this first example. Let's say we use a 5th degree Taylor polynomial to approximate sine of 0.4. So to do this, we need to know what the Taylor series for sine of x is, which we have used many times already. That is factorial plus x to the 5th over 5 factorial. They said 5th degree, so I go out until the power of x is 5. From this, let's make, minus dot, dot, dot. And from this, let's make the 5th degree Taylor polynomial. So that's what I was just talking about. That's x minus x cubed. Oops. Sorry about that. That was auto. X cubed over 3 factorial plus x to the 5th over 5 factorial. 5th degree stops there. So here is our Taylor polynomial. And now let's use this polynomial to approximate sine of 0.4. All right, well, sine of 0.4 is going to be approximately plugging 0.4 in for every x. And let's find out what that is. All right, so plugging that into our calculator, we get this decimal here. And notice I go way out in the decimals because we want to get as accurate as possible. All right, for an approximation to be meaningful, we need to know how accurate the approximation is. So how close is our approximation to the actual value of sine of 0.4? So to do this, what we can do is take the absolute value of the difference between our approximation using the series minus the actual function value, and we take an absolute value because we like error to be positive. So we'll take the absolute value of this 0.3894 minus sine of the actual value of sine of 0.4, to see how close our approximation is. And I'll do that now. All right, and that error comes out to be 3.244 times 10 to the negative 7. So we get a really good approximation, even if we only go out to the 5th degree. We certainly could get a better approximation if we used more terms, but really a very nice approximation only going to the 5th degree. Okay, let's move on. So we just did that error. We found the error between our approximation and the function. We also refer to this error as truncation error. And the truncation error is the remaining part of the infinite series that is not used in the polynomial. So the truncation error is made or is created by the rest of the series. And the rest of the series is also called the tail. Okay? All right. So now let's talk about truncation error. We're going to look at a geometric series, which always makes life easier. We're asked to find a formula for the truncation error if we use 1 plus x squared plus x to the 4th plus x to the 6th to approximate 1 over 1 minus x squared over the interval from -1 to 1. All right, so they truncated this geometric series. The actual series would be 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th plus x to the 10th, and so on. So they truncated it right here. And they're using that to be their approximation for this function. So What's nice about a geometric is the truncation error of a geometric is a geometric series itself. The rest of this is its own geometric series. So we certainly can find the sum, or the actual value of the error, by finding the sum of the tail. With a geometric, the sum is a sub 1 over 1 minus r. And for the tail, our a sub 1 is x to the 8th over 1 minus, in this case, our common ratio is x squared, so it's 1 minus x squared. And when we're doing error, we like the error to be positive, so we would take the absolute value of that. So that is the function that represents the truncation error. So if we were looking at this series at x equals 0.5, our approximation would be 1 plus 0.5 squared plus 0.5 to the 4th plus 0.5 to the 6th. And then our error would be 0.5 to the 8th over 1 minus 0.5 squared. And again, we can only do this when it is a geometric series, because that's the only type of series that this summation formula works for. All right, so this idea of the tail helps us figure out the error that we are introducing by truncating a series. That tail is also called the remainder. And Taylor's theorem with remainder. Let's read this. If f has derivatives of all orders on the open interval I containing a, then for each positive integer n, and for each x in the interval, f of x is given as that Taylor polynomial. We've seen that all along. And it goes all the way up to as far as we want to, whatever degree we want to stop at when we make our Taylor polynomial. So what we're saying is that if we truncate a Taylor series at some degree, then what is left after that last term is called the remainder, or the tail, like we said before. And the remainder term is simply the next term after the one that we stopped. So the remainder term is the n plus first derivative at c. We're going to talk about c. That's a new letter to us. Times x minus a to the n plus 1 over n plus 1 factorial. So it's the n plus first term. So let's go through our terminology here. The first equation in Taylor's theorem is Taylor's formula. The function r sub n is the remainder of order n, or the error term. That is the next term after where we cut the polynomial off. For the approximation of f by p sub n of x over I. So that's when we are using the polynomial to approximate the function. It's also called the Lagrange form, or for the way that we will be using it, we will be using something called the Lagrange error bound. So we are going to be using this next term right here, which is this guy, to help us approximate an upper bound for the error. So the maximum error that can be introduced if we cut the polynomial off at the nth term. Okay, so let's see what we do with this. And the Lagrange error bound is written, so it's that n plus first term, and we take the absolute value of it, and we say that the remainder, which will be absolute value, is guaranteed to be less than or equal to the n plus first term at c. Again, we're going to define what that c is, times x minus a to the n plus 1 over the n plus 1 factorial. This is called the Lagrange error bound, and will give us an upper limit on our error. So let's do an example to help straighten this out a little bit. So let's say we have some series cosine x centered at x equals 2. So I've already written the series. It's cosine 2 minus sine 2 over 1 factorial times x minus 2 minus cosine 2 over 2 factorial times x minus 2 squared. So to make this, I just used that Taylor series generator, where we use the kth derivative at a times x minus a to the k all over k factorial. So we use that to create the series. And now we want to use a third degree Taylor polynomial, so we'd be cutting it off here at the third degree, to approximate cosine of 2.2. What is the Lagrange error bound for this approximation? So what's the biggest value of the error if we cut this off at the third degree. So to be able to figure out what's going on, we need to know what all these letters mean. So n is the order of the polynomial that we are using for our approximation. So we're doing a third degree, and so the third order would be what we use the third derivative to find, and so our n is 3. N plus 1 is just add 1 to that. So we're going to be using the fourth term, or the fourth order term, to help us determine our error. X is the value that we are approximating, the x value inside the function. So that's 2.2. A is what we are centered around. That is 2. And C, this is the new value. So we need to find the C value that will make this absolute value statement as big as it can possibly be, that will maximize the absolute value of the n plus first derivative. And so sometimes we have to actually look at that fourth derivative to find out what value we're going to choose to maximize the Lagrange error bound. So the n plus first derivative is the fourth derivative in this case, because n plus 1 is 4. So we're looking at the fourth derivative of cosine x. Well, the fourth derivative of cosine x is cosine x. And cosine x is negative and decreasing between 2 and 2.2. So we have to think about what value we would choose. So let's look at the cosine curve. And we are interested in the interval between 2 and 2.2. So our fourth derivative is right here in that interval. And we want to choose the value in this interval from 2 to 2.2 that would maximize the error. So when we do this, we want to pick the value that is furthest from the x-axis. So at 2, we're up here, and at 2.2, we are further from the x-axis. That will give us the largest absolute value in this interval. So in this case, we would choose our C to be 2.2, because it will maximize the distance from the x-axis. And that will help us maximize, that's the biggest value we can put in to our Lagrange error bound. So when we look at functions and we're trying to decide what C is, if the n plus first derivative is strictly decreasing in the interval, then we would choose, so if we looked at this one, we would choose A to be our C value, because that's where we are furthest from the x-axis. If in the interval between A and x, if the function is increasing and above the x-axis, in this case we would choose x to be our C value. And in this case, between A and x, between here and here, we would choose C to be our C value, and that is some point in the middle. You'll either be given information to allow you to choose C, or it would be obvious that the function is increasing or decreasing on that interval. So for our case, we are going to choose our C value to be 2.2, because that's what's going to maximize that Lagrange error bound. So we're going to choose 2.2 right here. And now we're just going to plug in and find that Lagrange error bound. We're finding the biggest Lagrange error bound, R sub n, which was 3, because that's the order of the term that we cut the polynomial off at. The absolute value of that will be less than or equal to the absolute value of the n plus first derivative, so the fourth derivative, which we already saw. If we start with cosine, first derivative is negative sine, second derivative is negative cosine, third derivative is sine, and fourth derivative is cosine. So the fourth derivative is cosine. We want it to be evaluated at C, so cosine of 2.2 times x, which is 2.2, minus A, which is 2, to the n plus 1, so to the fourth, all over 4 factorial. So this is our error term that we're finding to help us get our Lagrange error bounds. We're going to plug in and find out what that value is going to be. So when I plug that in, I find out that my Lagrange error bound is guaranteed to be less than or equal to 3.923 times 10 to the negative 5. So that's the maximum that our error could be if we approximated, cosine of 2.2 using the cosine series out to the third degree. So that is how we are going to be using that Lagrange error bound. Let's do a little more practice with that. Okay, so here, use a fifth degree. So highlight the information that's going to be helpful here. Fifth degree Maclaurin means centered at 0, polynomial to approximate e to the 0.7. Then find the Lagrange remainder. All right, well, the Maclaurin series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial. We want the fifth degree Maclaurin polynomial. So we're looking at that. And let's call that p of x because that's the series we are going to use. And we would call it p sub 5 of x because that's the fifth order or fifth degree in this case. And if I want p sub 5 of 0.7, then I'm going to plug 0.7 in for each of my x's. These are factorials. Plus 0.7 to the 5th over 5 factorial. I'm going to go and find out what that value is. All right, so we get 2.0135714117. Now, then find the Lagrange error bound. So we cut this off at the fifth degree and fifth order in this case. So we are looking for r sub 5 is going to be less than or equal to, well, we need to identify all of our letters, n plus 1, x, a, and c. So n is the order that our polynomial is, 5, n plus 1 is 6, x is the value at which we're evaluating it, so that is 0.7, a is where it's centered, so that is 0, c is what we have to figure out. So we want to look at the n plus first derivative, so that would be the sixth derivative. If we write it like this, sixth derivative of x when our function is e to the x. Well, we love e to the x, it makes our life easier. So if our function is e to the x, then the sixth derivative is also e to the x. And we are interested in the interval. The interval that we work with is always between a and x. So we are looking at e to the x between a is 0, that's a, and x is 0.7. And e to the x looks like that. So when we look at this, we are increasing and above the x-axis in that interval. So our choices are a and x to choose for c. And at the x value, that's where we're furthest from the x-axis. So we're going to choose our c to be 0.7. All right, so now we're going to plug in. We need the sixth derivative at 0.7 times x minus 0. Oops, I know what x is. 0.7 minus 0 to the 6th all over 6 factorial. So that means our remainder term is guaranteed to be less than or equal to, well, the sixth derivative of our function is e to the x. So this would be e to the 0.7 times 0.7 to the 6th over 6 factorial. And I'll find out what that is. So that comes out to be 3.290 times 10 to the negative 4. So our error is guaranteed to be less than or equal to that value. Okay? This is kind of a funny one, and really more for demonstration because we end up using e to the 0.7 in our calculation. But it nicely demonstrates how to use that Lagrange error bound. All right, let's move on. Okay, so we have another one here. Let's take a look. Selected values of f and its first four derivatives are indicated in the table below. The function f and its derivatives are decreasing on the interval from 0 to 4. So all of our derivatives are decreasing between 0 and 4. So let's note that. And let's see, write the third degree Taylor polynomial for the function about x equals 3 and use it to approximate f of 3.1. Okay, so this is actually nicer. They've given us all the derivatives. So we're using our Taylor series generator. We're going to have the kth derivative at 3, that's the x value that we're interested in, x minus 3 over, x minus 3 to the k over k factorial. We are centered at 3. So we will take the zeroth derivative, which would be 12, times x minus 3 to the 0 over 0 factorial, minus 31 times x minus 3 to the first over 1 factorial, minus 48 times x minus 3 to the second over 2 factorial. What did they want? Third degree. Minus 81 times x minus 3 to the third over 3 factorial. That is our third degree Taylor polynomial for f of x about x equals 3. And now we need to use it to approximate 3.1. So that means I will we'll call this p sub 3 of x, and I need to plug in 3.1. So we're going to get 12 minus 31 times 0.1. We're plugging 3.1 in for each x, minus 48 times 0.1 squared over 2, minus 81 times 0.1 cubed over 6. So we are plugging 3.1 in for each of those x's. I'll find out what that is. All right, and I get 8.6465. So we've written the third degree polynomial and we've used it to approximate f of 3.1. All right, let's see what we're doing next. Same initial data, use Lagrange error bound to show that the third degree Taylor polynomial for f about x equals 3 approximates f of 3.1 with error less than 7 times 10 to the negative 5, so less than 0.00007. Okay, so Lagrange error bound. We went out to the third degree, third order, so we're looking at r sub 3, not 4. It's going to be less than or equal to the absolute value of the fourth derivative. Oh boy. At c, we'll figure out c in a minute, times x minus a to the fourth over 4 factorial. So we need to figure out all of our letters. So n is the order of the polynomial, so that's 3. N plus 1 is 4, which we've got here, here, and here. X is the value that we are evaluating at, so that's 3.1. A is what we are centered at, which is 3, and now we need to figure out C. Well, they told us that all of the derivatives were decreasing on the interval from 0 to 4. So, let's see. One sec. Okay, so our interval that we're interested in is between x and a, so between 3 and 3.1. And if all the derivatives are decreasing, on the interval from 0 to 4, then our fourth derivative is decreasing in there, and we would choose the left end of that interval. So we would choose our C to be 3. All right, so let's fill in what we've got. So we need the fourth derivative of the function at 3 times 3.1 minus 3 to the fourth all over 4 factorial. Well, we don't actually have the function this time, but we have a table of values. So the fourth derivative is right here. Evaluated at 3 would be negative 16. So we're looking at negative 16 times 0.1 to the fourth, that's a 4, over 4 factorial. So our error term will be less than, and I'll figure out what that is. All right, so that comes out to be 6.667 times 10 to the negative 5, which we're trying to show that the error will be less than 0.00007, which it is, 6.667 times 10 to the negative 5. So we have shown that it is less than that. All right. Okay. So homework is the problems that are in the back of this note packet that is in the folder for today's work on Schoology. All right, have a great day.